Hello, hi everybody. Good morning. Okay, so as I suggested, the survey paper is providing very basic concept of general object tracking. Okay, so I hope you to read the paper. And so this is the basic process of tracking we have discussed last week. Okay, so to track an object, so we normally, not always, it depends on the algorithm, but we normally follow these steps. So we in the beginning we have to build a model. So here the model means the model, high level model that is representing the uh, normally, tracking means moving, right? So the moving object, okay? So it can be face, or it can be body, it can be car, it can be animal, and something like that, okay? So to build the model, actually, we are assuming the object is already detected. So using some other, algorithm, such as, face detection, right? So once the object is detected using any previous methods, then we can build a model based on the detected object, reason. Okay. So this at the beginning, so it is becoming the first model. Okay, the first model of the moving object. For example, it can be a face, right? After face detection, then the next step is to make a prediction. So we are assuming the object is moving, the face is moving. So we are predicting the next status. So normally the status means, a position, but sometimes we also can predict the pose. If because when objects are moving, uh, the object can rotate or can be transformed in some way, right? So, or it can be rescaled. It can be get smaller. It can be bigger, right? So position, transformation, or rotation, scaling, or any change, we can make some kind of prediction. Okay. So what kind of prediction is depending on your algorithm. So if your algorithm is just allowing the position for tracking, then it can be just position prediction. Or if you want to track the pose, like rotation, scaling kind of stuff, then you have to predict rotation or scaling as well. Okay. So once the prediction is done, then based on the prediction, so here the prediction means it is not exact matching, right? So this is just prediction based on the previous status or the previous position. Okay, so we can use some prediction algorithms. You can use some very simple one or sometimes a little bit more complicated one. And for example, Kalman filter is one of the popular prediction algorithm. Okay, so have you heard about Kalman filter before? I think some of you have heard of it, right? Yeah. So Kalman filter is kind of popular one for prediction. Okay. So once the prediction is done, then based on the predicted, pose and position, okay, then we can try to match the object again. Okay. So here the match means, the matching between the built model, current model, and the predicted region of the image. Okay, we are basically comparing the model and the predicted area or predicted region. So if the model, so it is kind of, we can say it is kind of precise matching based on prediction, because prediction is just a kind of estimation, right? It is not, it can be, but it's not always correct. So we are kind of updating, fixing the prediction by matching the object again. So this in this algorithm, the matching is a little bit more precise process. It is taking more time than prediction normally. Okay. So after matching, we can get more accurate, status of the object. So the status means the position or pose, kind of rotation, kind of stuff. Okay. So if it succeeds, so we match the object correctly. It means I can see the same object in the predicted nearby, not exactly, but nearby the predicted area, predicted region. Then now we have a new object region, right? So it may be normally different from the previous one. So we can expect some kind of change in the matched, object, matched, region. So, for example, the position has been changed, so it's not a big deal. But sometimes it can, the object may change the pose. For example, when we are tracking face, the face may be a little bit rotated, right? So in this way, there may be some change. So we have to update the model again for a better, matching in the next, frame. Okay, so we have to update the model. Okay. By the way, when it fails, if we fail, okay, when it fails, it means, the system predicted the object in that position, but I cannot find the object. I cannot match the object in the predicted region, right? Fail. That's the meaning of fail. Then simply saying lost. I lost the object. I cannot find the object. Then we have to build the model again. It means, I cannot find the face in the predicted region. Maybe the face might have moved too fast, or maybe maybe disappeared, or whatever happened. Something happened, right? So we then, just in case, we are trying to build a model again. It means, for example, we can do face detection again. So in this case, the building a model, the model again from the beginning means we are searching the whole image instead of just the predicted region. So basically, we can do face detection again from the beginning. Okay, and then if we found any face, then we can repeat the same process again. Okay. So then, as we have discussed last class, what is the purpose of tracking? So especially in case of face detection, why do we have to do tracking instead of applying face detection in every frame? What's the advantage? Why are we considering, tracking instead of just doing face detection or object detection? Yes. Yeah. So basically, it is faster and more efficient, right? So it means this process is making prediction, matching object, update model, and this, iterative process should be faster than face detection. Okay. So by the way, if it is because of the algorithm you are using, okay, in case if it is slower than face detection or object detection itself, then it's not meaningful. Does make sense, right? So in the way, when we are designing the tracking algorithms, so we have to use much simpler features and simpler algorithm than object detection or face detection. Make sense? Okay. So in that sense, okay, so when we are building the model, so after the detection, right? Once I detected the face reason. So here, when we say, in case of face, when we say face reason, it means just a small area in the whole picture. So if we crop that area, it is just another image, right? But for the tracking, if we have to use the small image, again, just small image. If you have to deal with all the pixels in the small image, face area, it is much smaller than the whole picture, but still it is a lot of information. So instead of using the whole pixels, the image features of the reason, every pixel, we normally use features. So from the detected reason of image, we are trying to extract some features. And these features are becoming the model of the object for tracking. Okay, so finally, we can say the whole tracking process is actually tracking features of the detected reason. Okay, so here the model means kind of set of features. But depending on the tracking algorithm, right? Maybe you may want to use like template matching, very low level template matching for tracking. Then you can use the whole, pixels, just the image itself for tracking, okay? But it is not so common because it is, again, in terms of speed and efficiency, it is too much information for tracking. Okay, so we are not normally using the whole, pixels. Instead of that, we are trying to detect some features. So in the step of building a model, yes, exactly. So in the step of model building, so what we are doing is normally detecting features. So once the features are detected in this step, then all the following, steps. So making prediction, matching objects, update the model, they are all based on the feature. So the prediction is also about feature, and matching object, it means, matching features. So in that sense, matching object step is feature matching process, basically. Okay? The update model is feature updating. Okay? So prediction is the state estimation for the features. Okay? So this way, the features, what kind of features are we going to use? That is very critical selection and critical step, okay? Critical algorithm for a good tracking. So if we are using bad pictures, such as the whole pixels, right? Then, or sometimes we can also select colors, okay? So we can select some different types of features, right? So this feature selection is very important. Okay, what kind of features are we going to use? Okay, so today we will start to study, what kind of features can be very efficient and useful for object tracking. Okay, so let me show you this page first. Okay, so if you this picture, I'm now looking at page 13 of this slide. Okay, so this page is coming from the paper I suggested yesterday. So this paper, Object Tracking Survey. If you read this paper, you can see this kind of information, slide and picture. So this is just one example of how to represent the model. Okay, so simply what kind of features are we going to use? For example, if you look at the picture A here, so let's say we are tracking the human body. Okay, then in case of A, the feature we are tracking is just one point, center of the body. So I want to represent the model using this one center position, and I want to collect features based on this center position. It can be the edge feature, or it can be histogram feature, it can be color feature, whatever feature you select. Okay, so in case of number B, it is not just one point feature, so it is composed of many points that it is representing some important parts of the body. Okay, so set of point features. It is case of B. Okay, in C, it is a rectangle representation. D, it is a elliptic representation. Okay, so in this way, we can choose some different types of representation for the model. So this is talking about the model. Okay, in the step of model building, we can select one of them, and we can try to collect the feature values for this representation. Okay, so I don't want to discuss too much about these basic steps. Okay, just read the paper, and the paper is explaining some details about this kind of representation. Okay, so it's up to you to. That's why I gave you the task. Okay. Okay, so in this way, anyways, finally, in this way, feature selection is very important. Well, how to represent the model from the detected, object region. Okay. So, and based on the representation, what kind of features are you going to use? That is very important. So we will focus on the feature for today and tomorrow. Okay. So, in terms of tracking itself, what are the difficulties for tracking? So we can consider, we have to consider and we have to prepare this kind of difficulties. So loss of information caused by projection of the 3D world onto the image. So because basically the tracking is normally done based on the 2D images, right? So based like video frames or security camera. So normally they are 2D images. By the way, the object we are tracking is actually 3D object. So let's consider the case of car tracking. Okay, so we want to track the cars for kind of security reason, right? From the security camera. Then sometimes we can, when we are tracking the cars, so the cars are moving very fast. Sometimes we can see the left side of the car. By the way, the car rotated. So now we can see the rear side of the car. But sometimes you can see the right side, right? So in this way, because the 3D of car is a 3D object and it is projected onto the 2D image frame, right? So we can see a lot of variation. So from that kind of variation, we can lose some information. So this kind of information loss means like the initial model we have been tracking can be lost, okay, or can be cannot follow the object anymore, right? Because of the too much variation. Yes, exactly. Okay, Yeah, so this is kind of loss of information. Okay, so it is happening a lot in real world, and it is kind of very important factor we have to consider when we are designing the tracking algorithm. So sometimes, for example, we try to make the model for some multiple poses. For example, in case of car, oh, I want to train the left side of the car images, right side, and the rear side and front side. And in the algorithm, we can apply all the models instead of just using one model, considering this kind of projection of 3D image, 3D objects. Okay, so in this way, we can try to solve this problem. Anyways, this is one difficult part of tracking. Okay, and the other one is noise in image. It is very general, kind of problem, and complex object shapes and motion. So if the object is not a simple shape, very complicated, then it is getting more difficult, right? And the motion of the object is not so kind of simple. So for example, cars are driving one direction. So it is very simple, right? But if cars are driving like as a kind of making some rotation kind of stuff, the motion can be complicated, right? Complex. So if you have to track the kind of UFO, right? For example, then the motion can be very complicated and unexpected, right? So in this way, that kind of complex shape or complex motion is making the tracking difficult. So the complex shape is also related to this kind of shape, like non-rigid or articulated nature of object. So the object is not a kind of rigid object, and it is very articulated. So it means, it is composed of many parts. They are moving independently, right? So human body is a kind of, articulated object. Okay, yeah, right? So it is getting more difficult. And another one very strong and difficulty is the occlusion. Because in real life, when objects are moving, they can be occluded by other objects, like the wall or some other cars, right? So in this way, occlusion is kind of, because when occlusion happens, then it means we can lose the object, even though the object is there, but we cannot see the object. Okay. So in case of full occlusion, we can just say, oh, the object has been disappeared from the scene, right? It can be a kind of simple, decision. But especially in case, the object is partially occluded, it means we still can see the object, but we cannot see the whole object. Okay? So in case of human body, we can not see the left part, left hand, left arm, left leg of the body. You just can see the right side, right? So it is kind of, partial occlusion. So partial occlusion is difficult problems because mostly when we are tracking, we still want to track the object even when the partial occlusion happens because we know the object is there, right? So we don't want to miss that kind of information. So we have to consider the occlusion. And sometimes this kind of occlusion can be very temporary. So at some point, they are occluded by other objects, but after some frames, we can see the whole body again. Then how can we deal with this kind of information? So this is one important factor of the tracking. Okay, and illumination change is also another important issue. So for example, we are with the camera, security camera is outdoor. Then the sun is rising and setting in the evening. Then the illumination and overall color or brightness of the image change. Then it can affect the brightness and color information of the object. So for example, if you are using color feature to track the object, by the way, at some point the color of the object can change, right? Then we can lose the object. We may fail the tracking. Okay, so this is also kind of important factor we have to consider. Okay, and one more final difficulty is real-time processing requirements. We are normally dealing with the multiple frames, right? Video frames kind of stuff. Sometimes we just need to process and do tracking for the video frames as a kind of offline system. So, for example, for the stored video, we just try to track the object inside the video file. Okay, it is not a kind of real time. It needs to be fast enough, but it does need to be real time. By the way, if you are developing a very online security system, they can detect some or track some suspect, kind of suspicious, body. It can be a kind of, for example, terrorist, right? Then it should be real time. So that when the camera is capturing the image, you should do the tracking at the same time. Okay, so we have many applications requiring real-time tracking. So the real-time requirement is making it very difficult to implement this kind of tracking algorithm because it should be very fast. Okay, so you can not use any complicated algorithms. Okay. Okay, so because of this kind of difficulties, if we have to satisfy all these, variations and difficulties, it is almost impossible to develop the tracking algorithm. So normally we are giving some constraints to make the problem of tracking more realistic to implement for implementation. Okay, so first of all, we are assuming almost all tracking algorithms assume that the object motion is smooth with no abrupt changes. So it means the motion is not so much complex. So it means we cannot track like a UFO kind of movement. It's here and there, it's very suddenly, it cannot be tracked, right? So we are not tracking that kind of object normally because tracking is almost impossible. Okay, so the linear kind of movement is the easiest one. But even though it is non-linear, but still every frame, so we are between frame and frame, we are assuming the movement is not so much abrupt, very smooth. Okay, so this is one very important constraint. Normally, when this constraint is not satisfied, then tracking normally fails. Okay, and the other strong constraint is like it is also related to the motion, and the other constraint is object motion is assumed to be constant velocity. So actually, it is a kind of a little bit strong constraint. Like we can assume a velocity of the movement of the object is constant, but in reality, it's not possible, right? But we are just assuming that it's not exactly constant, but it means the velocity is not changing so much. Okay, so this is another constraint. And the prior knowledge about the number and the size of object or object appearance and shape can be another constraint. So for example, we can give another constraint like the size of object is like this. Okay, so between 10 and in terms of the width, 10 and 20. Okay, so it cannot be less than 10, something like that. Okay. And the appearance or shape of the object should be like this. Okay, So this way, we also can provide some prior predefined, kind of objects. So these are just kind of example of constraints. So we are not using all the constraints. It depends on the algorithm and application. Okay, so sometimes we use this constraint, sometimes we use the other constraints, or sometimes we allow more, variation, something like that. Okay, but still, in any ways, we still have some kind of constraints. Okay, so the first one, like smooth motion, this is very common constraint. Okay. Okay, so you have a question. If someone is walking and suddenly if he stops to running, will not work. Okay, so again, it is depending on your application and your algorithm. Okay, so your application is like, oh, you have to detect and track this kind of human body. Okay, walking, and we also have to allow, we also have to detect the kind of motion like running. Okay, then if you that is the requirement of your application, then you have to design and develop a tracking system to track that kind of motion, so even though the motion is not smooth. Okay? But still, the running, in case of running suddenly, right, walking and running, so the movement is very there may be some big change in terms of the movement and velocity. So if your algorithm can deal with that kind of movement, then it is okay. Okay. Dancing, yeah. So this is another case of very big, change, right? So it is a little bit more challenging task. It may not be easy, not in terms of speed, right? So even though we're dancing, the movement, the speed of movement itself may not be so big, but in this case, what can be the biggest change? It can be the pose, right, or shape of the object. For example, the human body, right? It can change a lot. So it is about the articulated nature of objects, right? Is that right? So because human body is so articulated, when we are dancing, the every part, our hand, arm, legs, they are kind of moving very differently, very separately. So the shape of and appearance of the object is changing a lot. By the way, the model we are representing the human body and the features we are using is very good enough to satisfy this kind of complicated articulated change, body change, shape change. Then we can track the body. For example, let me show you. Yeah, last class we discussed the Kinect system, right, as an example of tracking. Okay. Anybody has tried Kinect? I think many of you already might have experienced Kinect, right? It is very popular. It has been very popular, right? So anyway, so Kinect, you might have experience, right? Kinect can track your body movement very precisely. So when you jump and you are moving your hands and you are kicking, it can recognize that kind of motion because Kinect tracking, a Kinect system is designed and developed in the way. Okay? So it is not just using 2D image, it is also using range data. Okay, so in this way, if your system is designed to and have the capability to understand and track such a kind of very precise motion of the object, then it can be possible. But it's not easy. It is getting more difficult. The problem is getting more difficult and more expensive in terms of calculation time and algorithm. Is it clear? Okay, so Okay. So there was some general issues about object tracking. So first of all, to start the tracking algorithm, tracking study. So we have to understand about the features. The first step is how to build a model. Okay, the model is how to represent the object for tracking. So that is based on features. So what kind of features can we use? Okay, so let's discuss more in detail about the features for tracking. Okay, so I want to move to the next slide. So I uploaded the tracking tool slide in the system. So in the content folder, so you can find this slide. Okay, so interest features, point features. So this is kind of one example of the features we can use for tracking. Okay, it's not everything. It's just one example. By the way, but still it is one of the popular approach in modern tracking algorithms. So we're focused on this interest point features. So in some sense, we call it as interest features or interest point features because these features are composed of points. Okay. Okay, so let's consider this situation. Very simple, much simpler situation than human body. Okay, so if we want to track a book, so this is a book. So do you think it's easier for tracking than human body? Tracking the book itself? Why? Why is it easier than human body tracking? So based on the concepts of tracking we have discussed. Oh, it is gonna move. Yeah, I'm assuming that in this case the book is moving. Okay, so somebody is holding the book and it is moving. The guy is moving the book. Okay, so we are not tracking the guy, the people. Instead of the people, we are tracking the book. So it is moving actually. Features are not changed. Object is not changed. Shape is constant. Yeah, very good. Okay, looking so much information. Okay, yeah. So the feature, as you said, as you can, straightforwardly see, the object is not changing a lot. Looks like it's not changing a lot. By the way, so let's compare these two images. The left side, this is kind of very clear book. On the right side, okay, so let's say, just, as an example, this is the next frame. So we have to track this book between these two frames. Okay, so do you think the features of the book is changed or not changed? Was it changed? Mm-hmm. What kind of change? You can see here. Not changed? Yeah, so there's some different opinion, right? Somebody think it changed, somebody's not changed. So if you think it's changed, what kind of change? Oh, yeah, orientation and occlusion. Yeah, something like that, right? Yeah. So when you are saying changed, right? The book is rotated and occluded by other books. So occlusion can be also a kind of change, and even though it's partial occlusion, right? This is kind of partial occlusion. And the rotation also can be changed, right? What about scale, the size of the book? Do you think it changed? It looks like a little bit, right? May not be so much. Or, yeah, possibly the same. Yeah. But in reality, it may not be exactly the same, right? So in that sense, we can say, yeah, there should be some scale, right? Yeah, so we can straightforwardly say illumination might have been changed, right? Yes. We can say that kind of change, right? Rotation, occlusion, blah, blah, blah. So when you say not changed, somebody may think, it's not wrong, okay? Somebody may say, oh, it's not changed. In that case, when we say not changed, there is no change. What kind of change do you mean? What kind of change is not done? Why do some guys, may think, it's not changed? Why? Mm-hmm. Yeah. Yeah. The features, yes, yeah, yeah, good answer. Thank you. Images are not changed on the book, right? The images in the book look the same, right? Oh, they have the same picture in the front page, in the cover, right? So it's not changed, and features is not changed, right? Okay, so in that way, in case of human vision, so our vision, we are processing the information in very high level. Yeah, so we are processing the information in the very high level. So the picture on the left picture, like even though some part is some parts of the book is occluded, but for some parts of the picture, like this part, the lower part of the book can be seen in the right image, right? So in this sense, the picture is not changed. So there is no change. The other one is like, this book is rigid body. So do you know the term rigid body? So let me type in rigid body. This is very good example of rigid body. Okay, yeah. So the shape is not changing, right? So it looks like a rectangular shape of object and very rigid body. So it means the body itself is not changing. In case of human body, again, articulated body, right? Not rigid body. Then every part of the object can change the shape, right? But in case of book, there is no chance, any part of the book change unless we, just intentionally bend or intentionally tear out some parts, right? Yeah, so that is rigid body object. So it looks like the changes not so much. The shape itself is not changing. Okay, but still we have the shape change, right? So on the left side, it was kind of upright rectangle. On the right side, it has been rotated. So in terms of two-dimensional image, the shape has changed, right? Because of the rotation. Okay. But in terms of 3D space, it's not a change. The shape is just the same, just rotated. Yeah. Okay. Yeah. So in this way, when we are considering the change, right? It depends on, what kind of change you are talking about. Okay. If you are considering the 2D image change or color change, what is the feature you are talking about? Okay. So based on the features we are using, we can say it is changing, or sometimes we may not say, oh, it's not changing. Okay, yeah. So now let's focus on these two cases, two images, the left side and right side. So these are, we are assuming these are two consecutive image frames. So we have to find the changed transformation or position of the book from the left side to the right image. So in other sense, in the second image on the right side, for example, we have to find the model, the book model of the left one. So let's say, oh, this upright book is a kind of model we have constructed, okay, based on kind of any previous, detection or whatever aggregate, okay. So now we have very clear book image on the left side. So this can be used as a model. And on the right side, in the following frames, now we want to predict and match the model. Oh, it is rotated and occluded, but it is here. So we want to match the object, the book, in the right frame, like this. Okay, so to do this kind of matching, then after matching, we can update the model and we can track again, right? There's a kind of iterative process. So first of all, we have to match these two objects. Okay, so to match this object, we have to represent the model, the book model, using some features. So we cannot use the whole pixels. It's too inefficient. Okay, so what kind of features can we use? Okay, so a little bit different but very similar application of this kind of feature matching is, another example is panorama building, application. So I think most modern phones, Android or iPhone, they are providing this kind of features with the camera, right? You can take a panorama picture, right? By scanning your camera very slowly and carefully, then you can take this kind of panorama picture. Have you tried, any guys? I tried just a few times. Is it working? So in this case, what happens if you move very fast instead of very slow, movement? Then sometimes I experienced kind of, some kind of failure. Or they say, oh, it failed to generate the panorama, or it may generate very strange image, right? Instead of this kind of very smooth and kind of panorama image. Okay. So every frame, when you are moving the camera in the panorama kind of mode, then what is happening is, in every frame, every consecutive frame, they are doing some kind of feature matching. And then they try to stitch every frame again and again to generate this kind of panorama picture. Okay, so in this sense, this process is representing the step of image matching, feature matching very well. Okay, very similar technique also can be used in tracking. Okay, so anyways, this is very popular application of feature matching. Okay, so let's discuss about feature matching in this sense. Okay, so again, this is another example of two different pictures, two consecutive frames. Okay, I'm now moving my camera. It can be security camera or iPhone, Android, smartphone camera, digital camera, whatever. Okay. Then the left one is the previous frame, the first frame, and the right one is the second frame. Okay. So how can you guess? How can you guess? You move the camera. How did the camera move? Can you guess the movement? How is it? Is the camera moving now? From left to right? Yeah, so it looks like, yeah, we can recognize that, right? We can process and we can recognize that. The human vision can determine, oh, the camera is moving to the right, panning, right? So panning to the right direction. So how can you determine that? How can you see that? Which part of the image can give us that kind of information? Yeah, that's right. Yes. So, yes, exactly. So the peak of the mountain. So we can see the same mountain peak, right? So this area in the left image can be matched to this area. That is what we can see. Very then what about the sky? Okay, so let's consider the sky area. Okay, so what about this area and this area? Also, maybe this sky region may be the same, right? But why we cannot say, we cannot recognize that kind of movement based on the sky? So it looks like it's not giving us any information, right? How can we say that? So we just know, right? Because human vision can understand it very quickly, but practically, precisely, why? The same color, so you can say same color, okay? So technically, we can say, there is no feature. Okay, it is about feature. So when I want to detect some feature, so here the feature means something, that can represent the reason or the object very distinctively. So in case of the sky reason, the blue sky, so we have the same blue sky on the left image or right image. So by the way, the sky regions are not so much different from each other. They look all the same, not exactly the same, but very similar each other. It means, yeah, they are not significant. They are not, in other words, they are not distinctive. Okay. So first of all, the features should be distinctive. For example, the peak of the mountain. So this peak of the mountain. Let me change the color. Peak of the mountain here on the left image, and peak of the mountain on the right image. Okay. So this peak, there may be several multiple peaks, right? In one image, in the same image. But every peak, normally, in the worst case, there may be very kind of twin peaks, right? So they look the same. Then it's very difficult case. But normally, in nature, the peaks are different each other, even peaks, mountain peaks. Make sense? So for example, in the left image, this highest peak, there is a kind of looks like a second peak here, smaller one. Okay? Yeah, in this way, we can distinguish the peak feature in the image. Okay, so on the left side, we can see, for example, simply saying two peaks, right? One big one, one small one. On the right side, we also can see the same big peak and smaller peak here. Okay, then we can match these peak features very easily. Make sense? Okay, so once we have that kind of matching, so then it can be easier to get the information. Oh, how first of all, the mountain's point of view, how the mountain has moved. From mountain's point of view, the mountain was on the right side of the picture. And then the second image on the right image, the mountain is on the left side. So it moved from right to left, right? It means the camera moved actually left to right. Okay, so whatever, so it's different from, the point of view, right? So based on this information, how much, what direction, angle, okay, then we can stitch these two images, overlap these two images. Make sense? Okay, so let's have a break and let's continue for the details of this process. Any question? Now talking about the example of feature matching. Okay, so in case of building a panorama, so it is almost the same case of feature matching in tracking. Okay, so we have discussed about the concept of matching, how we can match the features. Okay, so in the real case, when we are using kind of features, so in this case we are considering point features. So first of all, to match the features, we have to detect the feature points in both images. In the left image, we have to extract some feature points. In other words, some good feature points. So let's say we have this kind of white dots, right? Here and there, and we have many points around the mountain. So again, we can see, there is no point in the sky because, as we have discussed already, the sky region is not so much distinctive, so we cannot find any good features, right? Any good feature in the sky region. So that's why we don't have points in the sky, right? And on the right image, we also can extract some feature points. So this is the detection step of feature points. We have to detect. We are saying not detecting object, okay? So we are just detecting features, feature points. In this case, we are using point features. Okay, so how can we detect the features? So we'll discuss the detailed algorithm later. Okay, anyways, for using any algorithm, there are lots of choices, lots of different algorithms. So using some kind of algorithm, we can detect feature points first. And then the next step is finding precisely, saying, we are trying to find the corresponding pairs. So here the corresponding pairs means, for example, the top, peak of the mountain, the big mountain, big, peak on the left image, and the top peak point of the right image, right mountain. So they are actually the same point, right? So based on the detected features, we compare each feature points, and we try to find the good correspondence between the feature points. So like this, top peak points. Okay, the peak point feature here, one point on the left side, left image, and the right image, another point. Oh, they look corresponding each other. So here the correspondence means they look the same object, same peak. Is that correct? Right? So in this way, for most of the feature points, we try to find the correspondence, like this one and the second, peak, and another feature point, this one and this one, blah, blah, blah. Okay, so this one and this one, they look the same points. Okay, but some of them, for example, on the left side of the left image, this side, right? So the point in this left side of the picture, of the left picture, may not have any corresponding pairs, because that area, that region cannot be, not just this one, more exactly saying like this. Now talking in the right image. Okay, so we have to give up this reason. So they may not find the corresponding pairs in the right image. Okay, so in this way, as many as possible. So even though some of them or many of them may not be matched, but we try to find as many as possible, corresponding pairs between these two different sets of point features from left and right, between left and right. Okay, so this is the step of finding corresponding pairs. So it's not always the same number of the point features. It can be smaller number normally. So once we have the correspondence, then between these two the set of corresponding pairs, then we can calculate using some another mathematical algorithm. We can calculate the perspective or some kind of transformation metric. How much has been moved? How much has been rotated? How much has been prospectively transformed? Right? So there are some kind of very well-known formula for that. So we can calculate the perspective kind of transformation between these two frames, images. Then finally, we can stitch the right image on top of the first one. Okay, so these are kind of very three important steps. Okay, so detect the feature points and find correspondence, and then stitch and align. So in this case, the third step, the last, aligning images, is not necessary in, object tracking. But the first step, detecting feature points and finding correspondence, is a kind of common steps for object tracking as well. Okay, so in this sense, detecting feature points is one important step, and finding corresponding pairs, it is kind of matching. So we normally say it is feature matching. Okay, so detection and matching features are very important task. So stitching alignment is very straightforward step, easier step. Okay, yeah. So we need to focus on these two steps. How to detect feature points, how to find the correspondence. In other words, how to match the detected feature points. Okay, so then let's discuss, consider more about feature matching. So what kind of features can be matched well? So our purpose is to detect the features points and match the feature points, right? Then final goal is to match the feature points. By the way, the feature point should be good enough for matching. So let's discuss this case. So this one problem case. So we have again left and right, mountains. Okay. So the left small region is coming from the left image, the first image, and the right small region of the mountain, they look almost the same, but right one is coming from the second image. Okay. Now, so just to make the problem easier, just focus on these small regions, and between these two small regions, images, simply saying, we want to match the points. By the way, in this is just an example. In this example, using some whatever kind of picture detection algorithm, Now on the left image, we have 4 green feature points. Okay, just an example. Okay, on the left image. By the way, on the right image, we have another 4 red feature points. Okay, is that clear? Okay, then after this kind of feature detection, so next step is finding the correspondence, matching these features. So can you find any match between these green and red points? So the answer is already here, right? There is no chance, no pairs, right? So in other words, there is no chance to match. There's no matching. We cannot find any correspondence between these green and red points in this case, just in this case. So what's wrong then? Is the matching algorithm, the second step, finding correspondence, matching algorithm is wrong? Or the first step, detection is wrong. The algorithm. So which one? Which one is wrong in this case? Detection is wrong or matching is wrong? So we have 2 steps, right, for now. Detection and then finding correspondence. Finding correspondence, in other words, matching. Okay? So simply saying detection and matching of the feature. So which one is wrong? Yes. Thank you. Good answers. Yeah. So actually, even though we have very good matching algorithm, right? But in this case, we cannot match because the candidates are very wrong, right? So on the left image, we have the green point feature at the peak point. On the right image, we don't have any point there. Then there is no chance to match, even though we are using very high level, very good matching algorithm, right? So first of all, the detection is wrong. Okay, it is talking about the detection algorithm. So the first problem is about detection. So actually, we have to satisfy this condition. We have to detect. So in terms of detection algorithm, we have to detect same point independently in both images. So the same point, like peak of the mountain, okay, should be detected in both images independently. Okay, so that is very strong condition we have to satisfy for the detection algorithm. If we don't satisfy this condition, then this kind of wrong detection can happen. Make sense? Okay, so when we are designing and using the feature detection algorithm, we have to consider this condition. Okay, the same point should be detected in both images. Is that clear? In other words, we call this kind of detector that is satisfying this condition as repeatable detector. So here the term repeatable, it is more kind of formal and technical term. Okay, when we say repeatable detection, repeatable detector, it means the points are repeating in every frame. Okay, the top peak of the mountain point is repeating again in the second image. Make sense? Okay, so in this sense, we call this kind of detector, not this case is wrong, but when we satisfy this condition, then we can say it is repeatable detector. It is kind of, so in other words, it is kind of very strong condition. Okay, we should have a repeatable detector. If you the detector is not repeatable, like this example, then we cannot do anything. We cannot do matching. We cannot do stitching. We cannot do tracking. Okay, so in the first step of detecting the features, whatever features, right? Whatever point features, then we have to make it repeatable. Okay, so it's very important concept. So try to remember. Okay, so the feature detector should be repeatable. The algorithm should be repeatable. Okay, so I believe you now understand the concept of repeatable. Okay, any question? Is it clear? Okay. By the way, when we say repeatable, not all the points can repeat in reality. Okay, theoretically, we are expecting, all the points in the left image is repeating on the right image. By the way, as we have, if we see the bigger picture like this, okay, in this example of the whole picture, okay, instead of just the mountain, peak region, okay. Then on the left image, right image, even though we are using a very good detector, repeatable detector, but this left part of the left image, okay, the point features in the left part of the first image cannot repeat in the second image. It's impossible, right? Because we cannot see that reason in the second image. Is that clear? So when we say repeatable, it doesn't mean 100% repeatable. Okay, some of them may not repeat. It's allowed. Okay, make sense? So in reality, we cannot expect all the feature points repeat in the second image, the next frame. Okay, so what we are expecting is kind of rate, repeatability rate. So we can calculate the repeatability. For example, in this sample picture of the mountain. So the top peak, this one and this one, and another point, this one and this one. Oh, we can see 3 repeating pairs, 3 repeating correspondence, right? Okay, out of all 1, 2, 3, 4, 5, 5, feature points. Is that clear? So 3 over 5. Among, 5 feature points, 3 of them are repeating. So in other words, 3 of them has correspondence. Okay, so what's the percentage? It is 60% or 0.6, right? Okay, in terms of percentage, 60% of repeatability. Okay, so we call this number as repeatability rate, simply repeatability. Okay, we are expecting higher repeatability. Okay, higher one is better. Okay, so if you are developing a new detection algorithm for feature points, then you can measure your algorithm with this repeatability. If you are giving your algorithm is giving higher repeatability than other algorithm, then you can say, oh, my algorithm is better than others. Okay, so if you read some papers about feature point detection, then they are talking about mostly, not always, but mostly talking about this repeatability rate. So, my repeatability is better than the others, right? So that is very important measurement for the performance of the feature detection. Okay, so this is one very strong condition. Okay, it may not be 100%, but we need to have very high repeatability, feature detection algorithm. Highly repeatable feature detector in this way. Is that clear? Any question? Okay. So yeah, that is first one condition and problem one for image matching. Okay, so let's consider the second problem. Okay, so in this case, so let's assume we have very good repeatable feature detector. So on the left image and right image, green and red points, feature points. Oh, we have very repeatable. So what is the repeatability rate in this case? Anybody can calculate the repeatability in this simple case? Just an example. So yes, exactly. It is 100%, right? All of them are repeating. Oh, the top one, we have just 4, right? 4 feature points. So top one, the pick one, and other 3 all looks like repeating. So the repeatability is 100%. So we can say the problem 1 is satisfied, condition 1, in other words, satisfied, and it is a very good repeatable detector. Okay. So the next step after detection is matching. In other words, finding correspondence. So based on these good repeatable feature points, now we want to calculate the matching, the correspondence. So for example, on the left image, first image, for this right, feature points, one feature point, one of the green one. Oh, now we have repeatable detector. So on the right image, I want to find the corresponding pair of this one. So it should be this one. Okay, right? It should be, yeah, we can see that, right? Then how? Okay, for each point in this way, so we have to correctly recognize the corresponding the other one in the right image. Okay, so this is actually the matching problem. Okay. Then, by the way, on the right image, second image, we have 4 candidates, right? 1, 2, 3, 4 candidate points. So which of them is the corresponding one for the selected points? So we know which one, right? But how? How can the algorithm determine one of them as the corresponding one? So that is the matching algorithm. Okay. So how? What do we have to do to do this job very well? How can we make them, find the correspondence easily? Location. Yeah. Good opinion. Local location. Okay. Yeah. So sometimes a verification step. So sometimes we can also consider location, distance. By the way, you have to remember, this is just a small region of every picture. So the original picture was like this. Okay, so in this case, from the first image and second image, there were lots of change in terms of location and distance. So we cannot guarantee location or distance kind of information can give us any good information for this kind of correspondence. Okay. So once we have these point features, okay, points, the point location, okay, every location of every point that is, calculated using the previous, detection step, repeatable detector. Okay, it's good. Okay, for now, until now. By the way, to find the good correspondence, exact correspondence, then we have to use some information about every point. So the reason why human vision can find the correspondence very well is because, for example, at the peak, the pixel information around the peak and the information around this right another point, second point, they're different, right? So from this kind of different information around every point, so we can compare whatever it is. So there are many options. So whatever it is, so we can compare this, information around every point. Then we can say, oh, this one looks like more close or similar to these points, corresponding points. Okay. So finally, once we have the point position, then we have to calculate some detailed feature around the feature point. More exactly, not just that feature point. Normally, we are using some surrounding, pixels to calculate the feature. So we have to calculate some detailed feature, actually some numbers around every point. Does that make sense? And then we can just compare the feature values of every point, and the most similar one can be selected as the corresponding one by comparing the features. So more technically saying, we are calculating the distance of the feature from left to right for every pair. Okay, so like this pair, this one, this one, this one, this one. We calculate the distance, and we are selecting the minimum distance in terms of feature values. In other words, the feature vector. Okay, then we select the minimum distance feature value, and that points can be determined as the corresponding points of the selected feature points. Is that clear? Not the kind of physical distance. It is about the distance in feature. So, for example, if you are using color surrounding the feature points, then the color of the left feature and the color of the right feature can be compared, and which one is the most similar one, then we can select the similar one. It means the distance is smallest with the most similar, corresponding feature points. Is that clear? Any question? So as for the features, then what kind of features do we have to calculate surrounding around the points? Okay, so it is something we have to study as well. Okay, so we will see there are some options. Okay, so we have to study about that. Is that clear now about matching? Any question? Okay. So more technically and more in detail, okay, so this kind of features, sometimes feature is very, abstract, right? Very high level kind of term. So we are using this term, descriptor. So this is more technical and very common words for that kind of value around for every point, right? It is called as descriptor. So descriptor means, this is kind of number, not just one number, set of numbers. So we normally represent these numbers as a vector. Okay, number of vector of numbers. Okay, it can be sometimes integer, it can be float, depending on the feature. Okay, so this is called as feature descriptor because these numbers are describing every point. Okay, the feature, right? So in this sense, we call this as descriptor. So here the descriptor means, feature descriptor. So this is kind of description of the point. Make sense? So in this sense, we call it as descriptor, feature descriptor. Okay. By the way, every descriptor of, this every point should be different each other. Okay, let's say, they all have the same descriptor, same numbers. Then, when we compare the distance will be all the same because the values are all the same, numbers are all the same. Then we cannot find the correct correspondence. Okay? So in that sense, every descriptor should be different each other against, between, all the points, right? So more technically, we call this feature as distinctive descriptor. Okay? So they should be distinctive. It means they are different each other. They can be distinguished easily. Okay? That is distinctive descriptor. So in terms of the feature value per every point, we need to have distinctive descriptor. And one more condition is the descriptor, the feature vector, should be reliable. Okay, so anybody can guess what is the concept of reliable in this case? Why the descriptor should be reliable? What does that mean? So finally, the descriptor of every point, okay, so we will study how to calculate it. Anyways, the descriptor of every point should be reliable and distinctive. Yeah, does not change, right? So normally reliable, when you say, some system is reliable, right? So there is no big change, right? Yeah, exactly. So yeah, does not change. So it means, for example, the descriptor of the peak here, point, and the descriptor of the peak on the right image, the second image, we are expecting they don't change too much for the same point, right? Oh, in the best case, if they are exactly the same, doesn't change, they didn't change at all, exactly the same. Oh, in the first image for the peak, we got some descriptor. For the second image at the peak point, we got some descriptor. By the way, they are exactly the same, don't change. Then what's the distance of these two descriptors of the peak point? The distance is becoming, they're the same number, subtraction, distance equals 0. Is that correct? Yes, 0, right? Yeah, that's what we are expecting. But in reality, it may not be 0, right? Because the left image, right image, there are some kind of variation, as we have discussed already, right? So it might have been rotated a little bit. There may be some color change, illumination change. So the descriptor is changing, not exactly the same. But when we are saying reliable, it means that change is not so big. Okay, so that is the meaning of reliable. So for same feature points, we are expecting a reliable descriptor, and between other other points in the same image, not between two images, right? In the same image, they should be distinctive each other. So that is the meaning of reliable and distinctive descriptor. Okay, so when we are developing some matching algorithm to find the correspondence, then we have to provide some kind of descriptor function or descriptor algorithm that can be reliable and distinctive. Okay, so this is the second important condition, second problem 2. Okay, so finally, to develop a good, feature matching kind of algorithm, then we have to develop some good detector. Okay, so repeatable detector and reliable and distinctive descriptor. Okay, that is our goal. And when we are using some other algorithms, then you have to select some algorithms, they satisfy these two conditions. So these are very important conditions. Okay, so you should remember this concept carefully. Okay, so we have some question. Yeah, okay, let's repeat the meaning of the descriptor, because I have a problem of, okay, no problem. So descriptor, so it looks like a little bit difficult kind of word, right? Okay, but the descriptor is like, now we have already detected the point, right? The green point and red point properly. Okay, repeatable. Okay, is that clear? Then for every point, to do this kind of matching task, right? We have to compare the points, right? To find the good correspondence. For example, let's say we can use color. Oh, we can compare color. Oh, is this color the same as the other one, or different, or the same, right? So if you find not exactly the same, but similar color, then this point is same as corresponding to this point. Okay, so in this way we can use some feature, right? But in practice, more exactly saying, the feature means some value. So let's say in color, maybe we can use RGB value, three values, right, of every point. Simply saying. Okay, if you are just using gray, it can be like, just one gray value. If you are using edge feature, then maybe you can calculate the direction of edge and the magnitude of edge, if you are familiar to the edge operation. Okay, so this way every point can have, we can add some feature values. It can be 1 number, 3 number, 4 number, whatever, okay, depending on the features. So that is feature descriptor. So descriptor means, some kind of data, normally it's number, okay, some kind of number data that is describing every point. How do you say, okay, we have 4 points, right? 4 point features in every image in this example. Okay, then how can you describe every point? discrete number. Okay, so that is descriptor. Okay, yeah, so feature description. Normally it is feature vector. So in other words, we are using this term as well, feature vector. Okay, that is feature descriptor. Descriptor is more theoretical. I'm sorry, this type. Feature descriptor. Okay, descriptor is a more conceptual, word, and feature vector is very, low level and more practical representation. Okay, so it's very important. Okay, I want to emphasize, you have to remember this concept very clearly to understand the detailed algorithm. Okay, is it clear now? Any other question? Question? Okay, good. So remember these two important conditions, okay, about detector and descriptor. Descriptor is for matching. So once we have good descriptor, then the matching is very simple. Okay, matching is actually finding the best, most similar descriptor. Okay, so descriptor is about matching. Okay, so finally we need detector, good detector, and good descriptor. Okay, yeah. So based on these two basic and very important conditions, if we have this kind of good descriptor, okay, then there are some following other important concepts we have to satisfy for in terms of the matching. So that is the first one is rotation invariance. Okay, considering the variation of the object. So the mountain picture, right? So we can move the camera in any axis. So we can rotate the camera. Then in the second picture, the mountain might have been rotated a little bit. Okay. Then the descriptor should be rotation invariance. So, or the matching algorithm should be rotation invariance. So let's say this is an example, very simple example of the mountain peak. Okay, it looks like very simplified mountain peak in the left image. In the right image, this is the mountain peak. Okay, so it is rotated. Okay, then the descriptor of the left image point and the descriptor of the right image point should be rotation invariance. Rotation invariance, what's the meaning of invariance? So it means it's not changing, no variance, right? It's not changing per rotation, even though the image is rotated, but the feature vector, the feature descriptor should be the same, theoretically, not exactly the same actually, right? But it should be almost the same, similar, even the case of rotation. So the feature is not changing when the object is rotated. Make sense? That is rotation invariance. Do you think it's possible? Considering these two cases. Okay, so this mountain is rotated to a little bit right direction, right? Rotated. So for these two peak points, can we expect any descriptor that is not changing in both point features? Almost not changing? Okay, you think it's possible? Yeah, that's true, right? We have some algorithms. They are rotation invariant. But sometimes some features are not rotation invariant. Okay. So yeah, so we'll see now which one is rotation invariant and which one is not. Okay, so we'll discuss about the details later. Anyways, we need the descriptor rotation invariant. Okay. The second issue about the descriptor, another issue is, the descriptor, when in this case, well, let's see this example on the left image, we can see the kind of curve, big curve. On the right case, it is straight down, very small curve, becoming very small. Okay. Then the descriptor, if you calculate the descriptor with for this kind of size of region, because when we are normally calculating the descriptor, again, we can calculate the descriptor around the point, right? At the curve point, for example. So if we calculate the descriptor using this small region, on the right second image, we calculate this using the same size. Then, what about the descriptor? It can be very different because the scale has been changed a lot. Okay, so this is another challenging task, So we need to have the descriptor scale invariant. So even though the scale of the image change, we expect, it's not easy, but we expect the descriptor is still the same or still very similar. Okay, so this is another property, scale condition, scale invariance. So what we are expecting is we want the descriptor rotation invariant first, and then also scale invariant. Some features are rotation invariant, but not scale invariant. Some features are rotation invariant and scale invariant. So we have to consider these two conditions altogether. Okay. Okay. So let me go back to this slide. So in terms of these two concepts, rotation invariance and scale invariance, they are all about the descriptor. Okay. So when we consider the original condition again, okay, so descriptor should be reliable and distinctive. Then the concept of rotation invariance and scale invariance, what is that about? Is that about reliable or is that about distinctive? Anybody can answer? What is that about? Reliability or distinctiveness? Okay, so our answer it is about distinctive, this feature. Any other opinion? Another opinion, reliability. Okay, wow. Two different opinion. Okay. I'm sorry. But it is about reliability. Okay. So when we say rotation invariance, okay, so it means it's not changing, even in case of rotation. Scale invariance, or it's not changing for the same point in different images, right? So the descriptor is not changing. So it is about reliability. Okay. Yes, exactly. Okay, thank you very much. And I think that's all for today. Okay, we continue tomorrow about some details. What kind of features can be, reliable and distinctive, and how they can be, scale invariant or rotation invariance. How can we develop kind of, the kind of invariant features? Okay, so we discuss more in depth tomorrow. Okay. Okay. Thank you very much, everybody. So thank you very much for your attention and engagement. Yeah, thank you. If anybody has any questions, even after the class, please send me an email or Facebook group. Okay. Any last question or something? Is everything okay? Okay, great. Thank you very much, and have a nice day, and see you tomorrow. Thank you.